public. Okay. Any questions before we have start? Great. Okay. Dr. Robinson, now it's yours.
Oh, thank you so much for the introduction, Dr. Wu. I appreciate it. So, today I was going to try and talk about my journey. As Wu said, I went from I won an undergraduate degree in physics, but I was primarily a pilot for 20 years. And that progression through NLP, AI, and into some of the problems that I'm looking at right now. Okay, so I want to present this in 3 different parts and 3 different stages to describe why we're doing this and why it piqued my interest. A certain research paper that I've published in safety science, and then a little peek about what I see as the future challenges and how we really engage that into a new research agenda and how it gets pushed forward. How did I end up in this? In natural language processing was really a function of being placed as the safety manager at the university. And when I was in that position, I had hundreds of safety reports that were provided to us. And given that my undergraduate education, my graduate education, it was more a case of, I learned of these tools of natural language processing and wanted to apply them. And this grew into a research agenda and ended up in the paper I'm going to walk you through today. But there are a series of papers where I apply natural language processing and try and discover new ideas and associations in the data. So in part 1, I want to talk about safety. And of course, you probably very often see this first slide where somebody takes a dictionary definition of safety. The condition of being safe from undergoing or causing hurt, injury, loss. And that immediately brings us back to, okay, well, wait. We're defining this word safe. What does safe mean? And safe is free from harm or risk. But in of itself now, we've got back to risk being a complex thing. Risk is a probability of an occurrence. It's a probability of occurrence that's couched and understood in a social context. We have a cultural association with this idea of risk and what's acceptably safe. In statistics, we might say it's like some threshold value, 0.001, or 1 in a million perhaps. But of course, that's a culturally determined idea. So as we said in our opening slide, we know the words and the associations, and safety is a good example of that, but it's also seated in this cultural matrix. It's an odd word, an odd idea, in that we're also measuring by negation. It's what doesn't happen. And so we define safety when absolutely nothing happens. And you think, whereas the public might define, say, if you ask them, what's the safest airline? They'd obviously say Qantas, for the fact that it's never lost a commercial jet hull completely. And so that in that metric of safety, where things don't happen, we've got this definition here. But that obviously means that we have no learning events. We have no learning events, we have no events, period, to demonstrate that there is safety. It's simply the absence. So it gives us an idea where it's not. So what is it? Because as a practitioner, it's actually a process. And when I get on if I got on a plane tomorrow, whether it's Qantas or some other airline, do I know that that particular flight is safer as a result? Or is this just historical metric of things that didn't happen? So I'm going to define this as an active process, that it's about organizational learning. Safety is where we see something, we reflect on it, and then we act on it. And learning is a change in behavior as a result of experience. And as an organization, that's really what we're doing. We're seeing things that may cause problems that we mitigate, we remove, we get rid of it. And it's the practitioners that do that. As events come along, we make small changes to different levels of risk. We change the environment around and we engage it a little bit differently. And if you think about that in terms of the game of Tetris, these are all little challenges being sent to us. And we get to maneuver these little challenges, engage them, mitigate them, change them. And in doing so, we're going to fill a role, which is to diminish our risk. Whereas if we do nothing, if the participants are not active and engage, then the blocks build up. And of course, eventually you get to the top of the screen, all the blocks build up, game over. And it's a similar allegory if we look at our inherent use of risk. You know, we allow the things to accumulate, then bad things are going to happen eventually. So if safety is an active process, what we really need to do is engage the actions of the practitioners and understand what it is they do. And of course, if we have a reporting culture, one where they're providing these safety reports, they're providing a detailed understanding of what they're doing to fix the problem. So our warning us about near misses, deviations, emissions, and also reflecting on if we did things differently, this would be better, and here's how. And we summarize that as they tell us how safety happens. All we have to do is listen. Listening is not a particularly easy job. It's a big industry. It produces lots of data, whether it be the aircraft data or the written reports of all of the individuals that file them. And so that gives us a challenge of volume and looking for patterns within that. It's not feasible to really look through every single one, read through every single one. And so this is a challenge and where we can engage with natural language processing. The biggest database of aviation safety is NASA's ASRS, Aviation Safety Reporting System. That's been going from 1975 and has about 1.8 million reports from all aviation personnel. It's part of NASA and not the Federal Aviation Administration, so that it could be a non-punitive reporting system. So basically, you can file a report of an emission, a failure on your part, as long as it's not intentional violation of the regulations. They're going to reduce the penalties or remove the penalties for that error. And so since it's been going since 1975, we've got this big set of data. And of course, that emerges as a useful source of this kind of research. So where we apply natural language processing, we're basically taking text, symbolic things, words, letters, and transforming those mathematically. And when we transform mathematically, we can look at the patterns that emerge and try and determine what is going on. What does it mean? And so the practitioner can look at this and interpret and reflect and synthesize the data and try and make sense of the patterns, engage in a process of sense making to try and look into why is this actually happening? How is safety happening here? So in summary, I'd say that safety is an active process. We're looking at what are the tools in order to engage in this kind of activity to generate the safe environment. So let's have a deeper look at our research paper that I published in 2019 in Safety Science. This is a culmination of several different papers that looked at topic modeling and visualization in ASRS data. So what's topic modeling? It's a data-centric pseudo-taxonomy. So if you consider a taxonomy, we say, all right, I have all these safety reports. tell me what they're about. And we might select a series of different labels for those things. You might say, this is a human factors issue that they're telling us about. Perhaps they lost their situational awareness. They were having problems with the weather. They're all different topics, themes that make sense to us that we could define in a taxonomy. And the SRS taxonomy has all of those things. And what you end up with is, in that particular case, lots of entries being made in the human factors bucket. So we have a taxonomy, but topic modeling as a NLP process is a data-centric approach to that. So rather than a person thinking about it and saying, these are the defined buckets that I want to put my data into, we're going to do it from a data-driven process. This begins with the vectorization of the text. So we're going to change the text into numbers according to some schema. There are lots of different schema that we can use, but in essence, you're always transforming some character, sequence, or word into a numeric value, looking at an entire document, a sentence, and breaking that up into a sequence of mathematical objects, a vector. And I think everybody's probably done this with where you make a coding system with A equals 1, B equals 2, C equals 3. And then you can write something out. We're doing the same kind of thing here in vectorizing the text. When you do that, those elements of the text have a vector, and a vector points towards something. And if we have two vectors that point near to one another, they have something in common. There may be a reduced distance or a reduced angle, and we can define metrics on them. So where these documents and their vectors cluster together, they can form topics, and we can define them in terms of statistical objects or other kinds of mathematical objects and say they come together in this way based on the context in which they occur. And as was defined, this is pre-NLP language at the beginning, we know that a word by the company that it keeps. So where we see an occurrence of a word in one document with other words, and we look at the occurrence of that word in relation to other documents, we can start to build relationships and understand how each of those words connect. In addition, for this study, I did a temporal analysis of those distributions. So where you have how frequently do we have weather problems? How frequently do we have situational awareness problems? We can measure them. And so by having these clustered documents and knowing what topics they're distributed amongst, we can do that same thing over some time window. This particular study used a bag of words approach and latent Dirichlet allocation. So a bag of words is a count according to some kind of dictionary. So if you consider, if I get a vector, so turn left heading 180, left heading 180, that's 3 characteristics. If in the same report I said subsequently they said turn left heading 160, that would be left heading. And those 2 tokens or words would have a count of 2 because they occurred twice in that document. So the count of words is what this bag of words is. And it's called a bag of words because you lose the order of those words. But it turns out that it actually works really quite well in topic modeling. We're not trying to determine who said what or who did what, which requires some sequential information, but rather what it is that these people are talking about and directing us towards. So there's an interpretation that occurs, and because we're looking at it as a topic, the word order doesn't actually matter very much. The latent Dirichlet allocation is an elegant process for taking a distribution on a distribution, which sounds really complicated, and it is actually quite complicated. But if we read this, documents contain a distribution of topics and topics contain a distribution of words. So if you consider, if we had a document, if it was about problems with weather that I had to navigate in the airplane, you could say, you can imagine that one topic might be about weather. And it also contains information about the topic that we're going to call maneuvering. So our problems with weather in an airplane contain weather, maneuvering, these two topics. And each of those topics have a selection of words associated with them in a rank order. So what are weather topics? Oh, the word weather, thunderstorms, clouds, rain, visibility. On the other hand, our topic about maneuvering might heading, left, right, climb, descend. They'd all be terms that are associated with the two. So we have a document that contains these two topics, and each of these topics has a selection of words. And by working through our distribution, we generate a document. And the latent Dirichlet allocation process builds those distributions. So you have a distribution of topics and a distribution of words within those topics, which maps to something that is tangible and makes sense. One key thing about latent Dirichlet allocation is that we have to select the topics ahead of time. And that requires some experimentation to come through as to what's the best. You know, if you look through the literature, you'll find a big range from like a few dozen to hundreds in this study. So in this particular study, it was just focused on commercial operations. So Code of Federal Regulations, Part 131. That meant that the people involved were all professionals. The vocabulary was focused and the situations were common. It took a sample of data from 1995 to 2009, which gave us about 65,000 reports. The range there was probably 50 in the lowest month and 300 or 400 in the highest month. So for most months, it was a fair distribution. For the LDA, the sample was 200 topics. That was a balance between what was a rational, manageable number on the high end and something would have enough fidelity to pick out the topics. So if you pick very few labels, much like ASRS, his own taxonomy, you end up with everything going into one bucket or a very few buckets. So you've got human factors. It's the bucket that most of the reports go into. So here you select a higher number. In a prior paper, I justified why this is a good number, around 200, both from a mathematical sense and a practical sense. It gives you pretty high fidelity of these reports and your ability to discriminate. So it's 200 topics here, 200 different labels. The dictionary or the vocabulary was 9,000 words. So this is an experimental bit where you say, of these 65,000 words, they consist of hundreds of words each. How many unique words are there in this complete set of data? There are a lot. But how many of them are useful? If you consider words that don't happen very frequently, they're not actually that useful. We may get one report where the captain says the first officer's resolution was very erudite, but it's the only time that word occurs in 65,000 reports. It sits alone. It doesn't offer any information. There's nothing that we can tie it to between reports. So you get rid of those words that don't occur frequently. The same is actually true for the most frequent words in topic modeling. Words that are mechanical in the language, like I, thee, you, a, it. Those are all mechanics in the English language, and they really don't offer any insight as to what the topic is or what the theme of the discussion is. So you drop those two, the high frequency, the low frequency, and here the optimum by experimentation is around 9,000. I said that it was calculating the distribution of topics by document. So if a document was received and I have a probability distribution of which topics it pulled from, then the sum of the topic probabilities is 1. Because we have a document, it exists, so the probability sum is 1. So you take each of these topics, I have a probability of how much that document came from a topic. And I can use that to my advantage where I say, okay, the sum is 1. And so if I take vertical slices and I say, I want topic number 165, sum it for all of the documents in a month, I can then divide it by the number of documents and tell you what fraction of the whole corpus, the whole of that month, this topic was. So you got 200 topics. We have a distribution on those topics for every month, and it always adds up to 1 because these are probabilities. So we've got the model we built along this long time series and then quantize it into these blocks of a month. This data was then provided to 3 subject matter experts, myself and 2 others. They were both 737 captains, one at United, one at Southwest. One had previously been chief instructor. They were both flight instructors, and one had been was active military. So a broad range of experience. They were afforded the topics, the words, and the principal reports from each of those topics and each of those months. The toolkit is pretty commonplace now. This is Python as a programming language, the GenSim package for actually calculating the latent data slate allocation, Pandas for manipulation, which is a data frame manipulation software, and then Matplotlib for actually generating the graphs you're going to see. So let's jump into a graph and we'll look at the results. So across the x-axis along the bottom, you're going to see dates. Each of the points as we go across are 1 month's data. So there are about 180 points across here. On the left, on the y-axis, we've got this aggregate topic weight. That is the sum of topic 165 in that month divided by the number of documents in that month. So how many reports came through that month? What's the probability? Divide it. And so you think, okay, there are 200 topics. If they're equally distributed, that 0.05, okay, that's the mean. So this is a bit higher than the mean for all the topics. The thing that we see right away is that, oh, it's periodic. It definitely jumps up. And it seems to jump up in big peaks around July. And it seems to be very small around December, January every year. And if you think for a second and wonder, okay, these are all reports from the northern hemisphere, what could this be? This is a topic about weather. Specifically, it's about convective weather activity. The words that are most probable in this topic are weather, us, deviation, thunderstorms, air traffic control, would, told, miles, course. And as we go down the probabilities, there's also the word emergency. And it makes sense that it's periodic. It makes sense that the words are distributed as we'd expect. A priori, we would have thought, yeah, there's definitely going to be a topic about weather, because that's definitely a thing that pilots deal with. And so one of the acceptable ways in which we can validate a model is this exogenous approach. So we identify the themes that we expect to see in the data. You can do it ahead of time, you can do it after the fact, but you have to see some consistent level of modeling that reflects what we expect in the real world. What would your taxonomy be if you defined it? There must be an overlap in order for us to say this model is valid. In addition, because ASRS has metadata with it, we can make an association. So we know that If it's about convective activity, we know that convective activity has clouds because it's about the vertical motion of air and clouds get formed. So because this has weather conditions reported with it, we can associate the two and correlate the two. So here where the report said it was IMC, it was mixed marginal, so instrument meteorological conditions, did it occur with this being a primary topic? And the chi-squared here is 0. So there's a very strong correlation between the two. And it further validates our model and says, yep, it definitely occurs where it should do, and it makes good sense and good cohesive sense. I started by saying one of the words not on this list was emergency. And this was one of those events where you recognize the validity of seeing these models in context of what people say. So in prior studies, they did a lot of work in giving subject matter expert this set of words and saying, what does it mean? What's this topic about? And the trouble with doing that is it doesn't provide the context. And so when we looked at the words and we saw the topic, the one that I haven't included, which is emergency, we all sat there and thought, why is it about emergency? And when you read the reports, what is common, at least in the United States, is that you have to realize that air traffic controllers do not have control of military operations areas. And so there's an instance where thunderstorms near to military operations area restrict what air traffic control can easily do. And so they don't vector the airplanes into the military operations area, which means that they're pushing them towards the thunderstorms. Subsequently, the pilots are avoiding the storms that they're seeing on their radar and making a decision. And they're declaring emergencies such that they can make the turn into a military operations area. It isn't a dangerous thing to do because those areas are cold and the air traffic controllers know it, but they don't have the authority to directly vector them into it. So there has to be an exchange with military controllers, which they won't necessarily have the time to do, but in situ, the pilots have to make the decision and declare an emergency. So this was the first of those where it began to provide interesting results and surprise the subject matter experts. The next one started to pique our interest further. And this one, 159, was failure to intercept the flying approach course. The words associated with it were localizer, approach, ILS, runway, intercept, autopilot, glide slope, and course. As you read the reports, this revealed an interesting situation that I think everybody's been in, all the pilots have been in. You've set the airplane up for an approach. We've briefed it. We've put it all in the electronics, the radios, the stack, the FMS is all programmed. And then for whatever reason, air traffic control has to reassign a runway. And so you get a different approach. All of a sudden, you're very busy. I have to, I've got to change my plates. I've got to rebrief the approach. I've got to reprogram the flight management system. And depending on where that occurs, how busy we are, how bad the weather is, and in a Tetris allegory, we might be pretty high on the stack, giving us that one extra task, make things difficult. That might lead to a violation. So our failure to intercept the flying approach course, we got behind the airplane. It was a problem. And this is such a common problem that I actually found a YouTube video. So I'm not sure the audio will work on this machine, but what you're going to see here is the pilot say, very good, very good. The co-pilot just finished the briefing and the setup. Air traffic control is now telling them, okay, we're going to change the runway. And the pilot had a little giggle in his response to air traffic control. So first officer had set everything up beautiful. He said it was great. And now they changed the plan. And here you'll see our first officer now is going to start getting busy. They're going to change the approach flights. They're going to rebrief the approach. And you're also going to see the captain here in the video reprogram the FMS looking down. So everybody got really busy really quickly, and this is a situation where that can this failure to intercept the flying protocols can happen. What you also see on the graph is that there was a change around 2006, 7, and 8. There was a reduction and then a sudden increase in this topic. This piqued everybody's interest and was like, what was going on there? We checked the Federal Register where the laws are first published, and there was no apparent outcome. So this remains a mystery to us as to why this particular topic had an increase during this period. But it was an example where we all came back to it and asked, what is going on here and why? And people went away, looked at it some more, and tried to figure out what the problem actually was that generated this spike in 2007-8. Next one was warnings of automation conflicts. So this was a little bit more subtle, but in one sense, but more deliberate in another. You see from the graph that this is almost nothing until 2008 going into 2009, where it suddenly increases. The words are RAS, feet, rolls, altitudes, system, airspeed, probes, automated. And the RAS here is an abbreviation for the Runway Awareness and Advisory System. In 2008, this was introduced broadly across the Alaska Airlines fleet, and the pilots didn't like it, and there are lots of safety reports generated as a result. The video is actually a news report from the time. The devices yelled, on taxiway, to the pilot. So it keeps giving them these audio cues whenever they get to a runway, a taxiway, and cross it. In that one, it was the report was approaching runway 34 left. And the trouble with that is the audio sets a priority in the airplane. So it's in a stack of priorities. And where this message goes through, dependent on its priority, it can overwhelm the other communications in the cockpit. So the pilot reports for this, and their problem with it was that this system would make these auditory reports over the channel and inhibit the rest of the conversation with air traffic control. So it could be that they were given the instruction, line up and wait. They're coming through, taxiing across the threshold of the runway. At the same time, air traffic control gave them the clearance for takeoff, which they didn't hear because of this system, or they only heard portion of. And so this was causing significant consternation for the pilots at Alaska around that time. When it was introduced, it was done so without listening to the pilots and without seeing the results at the time. The other thing that came through and was engaged by the subject matter experts was the voice. Different people, there are different reporters, and they have different stories to tell. And they do so in a different vernacular. So where an air traffic controller talks about the flight situation, they say things like aircraft X, aircraft Y. And that's their common vernacular as they describe the situation. Pilots, of course, don't describe it in such terms. So it's a distinct difference between the voices and the words used by different people, different reporters in this. So the data contains the metadata about the qualifications of the reporter. So we're able to select for flight crew and air traffic control and look for the correlations between the incidence of the topic and this qualification. It turns out for many of those topics, there's a very strong correlation with the voice of the reporter, whether it be flight crew, air traffic control. There are also some predominant ones for maintenance. And that's surprising really because, remember, each document probably contains a distribution of topics, maybe one or more. So having a chi-squared match one of those characteristics means that it was a really strong and dominant topic. So this paper demonstrates several things. In the SME's view, the topics were coherent. It made perfect sense to them. They're engaged in the material and they saw that it reflected things that they expected it to in a good taxonomy. We're able to make note and identify what interventions or policy changes resulted in. So you could see RAS made a difference. It affected the way the pilots report and what they discuss and the kind of problems they were having. There were some surprises. Looking at these different trends, they found things that they weren't expecting. And it took some sleuthing and identification and research to figure out what those things were. Overall, this was about stimulating this active process or engaged. It was common during this period that one of the subject matter experts would show up in my office and, okay, can we analyze this data in a slightly different way? Because I think this is a thing. We can also say that common amongst many of these topics were automation. The way in which people interact with the machinery was a definite common theme of safety that we looked at. So that was this paper. But there was also a lot more data and for this with the 200 topics. So as I went through all of these graphs for each of these topics, I noticed a trend, and I think you'll all see it pretty obviously here. Come 2009, or the end of 2009, there was a change. These topics all fell off a cliff. They reduced to almost nothing. Very suddenly, coming into 2009. And there are three such topics that I found. And as I kept looking through the data, I noticed something else, and that was, there were two topics that about the same time jumped up in priority. So their occurrence went from almost nothing to being very prevalent. If you recall that my mean line is about 0.05, it means that it was nothing and then it was significant. So what is it? We've got this reciprocal clustering of topics. Something definitely happened in this period. And the thing that happened in consultation with another pilot was around 2009, end of 2009. So the ones that we saw drop off were related to flight crew. That 39, 109, 132 were flight crew reports. The ones that increased were air traffic control. So the reciprocation happened between different groups. And this was a result of the TAP program. So the Traffic Analysis Review Program is a system to monitor for loss of separation. So if two airplanes are in the terminal area, they have to maintain 3 miles of separation and 1,000 feet vertical, as I recall. So if the airplane's getting closer than that, we generate a report, a loss of separation event, and it gets investigated. Prior to the TAP program, this was done by air traffic controllers. They monitored it, they reported it, they instigated it. It was just them. But the TAP program automatically captured all of the data that was available in the system during that event and prior to it, including the audio. And then it pushes it all to a database. And then it gets investigated. And so what you can see is the results of that. And the results are significant because of what brought TARP about. It turns out that air traffic controllers at Dallas-Fort Worth were losing separation commonly at that airport. And what they were doing was systematically blaming the pilots for that. They were moving the culpability over to them because they could. This was brought up into federal record by 2 whistleblowers, and the report is actually quite interesting of what they saw and how they methodically messed with the pilots. And so when this came out, the FAA accelerated the TARP program by, I think, 2 years and pushed that into operation in 2009. And that's where we see this change. All the flight crew reports were related to clearances, departures, terminal area interactions. Air traffic control was describing these loss of separation events. So this was one that wasn't included in part of that paper, but was part of the same data study, and became very apparent to the subject matter experts that this was about culpability and a description of who is responsible and how that made a significant change. Part of this, the bigger study in our analysis, was really focused on seeing if there were changes over time as the result of laws or introduction of some system. But we didn't really see that significantly, but we did see that this change, this introduction of TARP and the change in culpability made a massive difference to the way in which people spoke. So if I were to summarize NLP and the application in this journey that I've been on and a number of papers written in this area, it provides pre-masticated data and mastication to chew up. So you're making something data that's easily digestible for the people who need to look at it and engage in it. So having these tools allows us to take all the data, review all of it, engage all of it. We can change our approach. Whereas ASRS has a fixed taxonomy that's been fixed since 1975. You can't really change it. But here with NLP, we can just reprocess the data with a different model. So we can change our approaches and see how they work. And given computational resources are not that high relative to computing power that we have today, it's really easy to do that. It's quick, it's simple. We can look for differences. We can find trends that we weren't seeing before. And of course, we can present the data in an interpretable manner. So off to our right is actually from 2014, a Google presentation, and it's about a visualization of clusters of written characters. So this analysis on a visual element and transforms it into a different kind of visual clustering. And each of the clusters are different numbers from 0 to 9, handwritten digits. And it just serves as an example that we can do these clustering techniques, and this interpretation and graphing can be applied broadly to different things, and we can still discover information. So our data illustrates understanding and gives us the opportunity to focus more on the tangible outcomes. What makes a difference in this? And the way I like to think about this is the numbers are evidence of thought, not a replacement for it. So that process of safety, being an active one and engaging people, is what's important. We can present a number, 0 accidents, but that doesn't really mean that the active process is ongoing. So it isn't, it's evidence that Qantas are doing their job in engaging in safety, but it isn't a replacement for it. It isn't the be all and end all for that measure. Okay, so I'm going to switch gears a little bit and change to our challenges for future research. And this covers a little bit about the kind of research that I'm engaging in right now. we think about why is NLP successful now? Why is it a common garden tool set? We've got economics, computation, and interdisciplinary research. NLP has gone on since the 1940s, 1950s. So there's lots of historical data, methods pulling from different domains. Economically, we have the internet of the last 30 years. Of course, the internet has changed our behavior as a massive economy all by itself and changes the rest of our economy. So even marginal gains in our understanding of language, and given that the internet is primarily written language, manipulation and understanding of that, even tiny gains have massive results and economically can be huge. Of late, we're pushing neural networks over onto graphics cards, a GPU. And that, for let's say, if you spend $300 on a graphics card versus a processor, you're going to see 50 to 100-fold increase in speed. So things that were not feasible before, that would have taken years, decades to train, can be done in days, weeks. Massive models, and that's what we're seeing right now is GPT-3 and stuff. Those neural networks are very big models with billions of parameters. So there's lots of investment, lots of power, and lots of research that have gone into that and doing this cognitive task, written stuff. Whereas our next domain is really to engage the psychomotor and the cognitive tasks, which is more what we see when we deal with high consequence industries and socio-technical systems. And of course, we've seen our lovely video of our scary robot from Boston Dynamics. And in this case, it's doing parkour. It looks very human in doing so. So it does this, it's got to understand the physical world. It has to visually process that and interact with it in real time. So the expectation is that we're going to do similar things with cars. And the Society of Automotive Engineers has level 5, which is fully autonomous self-driving. As a result, the engagement in robotics, whether it's in something like Boston Dynamics, or assisting the elderly or those with disabilities, we can engage robotics to assist that and work with the humans. And of course, we've also got Facebook's push towards the metaverse, which is using physical portions, our interactions, our movement, as well as this virtual realm. The trouble is that the real world is really poorly defined. And by saying that there's magic here, there really isn't. It's all in numerical methods. For all of our models that you build, they're not sentient. They're just trained on a lot of data. But training data is limited. So where we have edge cases in a high consequence industry, we have the result is very high risk. And you'll see from this video, and it's a fairly recent one with the Tesla Model 3, some shenanigans. You see very abruptly steered into the green bollard. And now the guy is looking at the damage on his car, his very expensive car, while it was self-driving. I don't know if you all, the drivers amongst you, looked at that, but as it went around the corner towards that green bollard, it pulled towards it. And at that point, I looked at it and went, ooh, I think it's going to interact with that. And it did. It's an edge case, probably. It probably hasn't seen a green bollard. You or I will look at it and go, oh, look at that ugly green bollard. That's dumb. And go around it. It, for whatever reason, and it's not an explainable reason, hit it. And of course, on the street, as in airplanes, that could have been a much bigger problem. It could have been a child. We can lose an airplane. So the risks are very high. So those edge cases are a massive problem. But the trouble is that our AI represents the facts and rules in a really narrowly defined way. It isn't flexible like people are. It doesn't have common sense. And AI does not. change with the situations over time. It can't do that. So it doesn't quite fit, and I guess I'm pushing up on time. It doesn't quite fit with the common parlance on this. What does the public think? They hear from Tesla that with your neural network and just visible light cameras, we're going to have full self-driving. We've heard we're going to have full self-driving since 2017, but we haven't got full self-driving yet. In fact, the news just came out that the head of AI at Tesla just left. And this is so poorly defined. The German government have told Tesla that you can't say it's going to do full self-driving because you've got no proof of it. And that's a public domain, this magic machine that can do everything. And the truth is it can't. And we see that in the way that we work with an autopilot in an airplane. It has a limited scope. It does a thing. In a psychomotor scale, it does the stick and rudder bit. It doesn't fly the airplane for me, but it does the stick and rudder bit. If I connect it to a flight management computer, it can calculate where the top of descent is, where I should hit a given waypoint, etc. And so reduces the cognitive task load on the pilots. And they have the choice to increase, decrease their automation as a result, and they can manage it. It has a culture associated with it. Whereas I say it doesn't fly the airplane. The popular view might be that it does, but as you train the flight crews, it's who's flying the airplane, because it isn't the autopilot. It's always one of the pilots who is conscious of the flight state of the airplane. Where are we going? And the final point is we've had it for a long time for this to be part of our culture. And as we think about this, people are our best resource. People are really good at common sense and looking at those edge cases and managing them. But the AI has the potential to improve our performance overall if we do it deliberately in a managed way. So we begin with the small tasks and the data-driven tasks. We're going to learn from the humans. And one of the things that comes out in this kind of research is that people are really general. People have these generalized tool sets and ideas about the world that the machines don't get. You train a model, it can do it better, this one task better than a person. But as soon as you generalize things, the model is useless, whereas people adapt really quickly. So that's something that's key that the technology and the models have to derive from people. In order to work with people, we have to identify their conventions, and some are totally arbitrary, but you have to follow some convention so that we can work together. And we need the better data to model the humans. Much of the data in aviation is just a data dump. I can give you all the flight state information from the airplane, but that doesn't tell you what the pilots are trying to achieve at the time. So it doesn't have an experimental framework to it. The AI should be interpretable and influenced by the humans. If I don't understand what it's doing, what is it doing now, comes out of my mouth, we failed. Also, if the actions of the pilots, the people interacting with the system, don't affect that AI, we've also failed because it should change its behavior. And so we end up with a cooperative paradigm overall. So I would say empower the practitioners and engage our resources and focus them on this symbiotic cooperative approach. Okay, so there are my 3 points. Safety is active. The numbers are evidence of thought, not a replacement for it. And in our next steps, we should empower the practitioners further. Thank you very much. Dr. Webb?
Oh, thank you very much. Thank Dr. Robinson's talk. And I have a little bit problem to get this system working properly. So I'm going to stop the recording now.